Open your notebooks to the next available page. As promised, we're going to continue practicing some of these visual patterns. So sketch out the pattern. Split your next notebook page into 4 quadrants. Recall those 4 quadrants are as follows. We want a verbal description, a sketch specifically of the 43rd step, some kind of graph, or right now probably a table where we look at the data, and then most importantly, an equation that will predict the number of blocks in any given step number. Step number n usually is what we're interested in. So let's get those 4 quadrants into our notebook, and then go. You've got like 5 minutes. Do we have a volunteer for a verbal description of this pattern? Isaac?
There's 3 blocks on the bottom and 1 block on the top of the far left block.
Uh-huh.
And then each step you add 1 block to the far left and 1 to the far right.
Yeah, I think that's pretty good. If I were not looking at it, I think I could reproduce the pattern pretty well that way. What I was thinking is start with 4 blocks in a sideways L. Then add 1 block to the left and 1 to the right, each new step. What about the 43rd step? What should it look like? Who's got a sketch for me of the 43rd step? Scarlett? Okay, so Scarlett is thinking, all right, so it's going to be this really tall L shape, right? And she's saying there should end up being 43 blocks here, 42 blocks here. Now, Scarlett, I want you to come back over to the picture. So this is step 1, right? This is step 2. This is step 3. In step 1, what was the arrangement of blocks on left and right? Like how many? 2 and 1, right? What about in step 2? 3 and 2. What about in step 3? 4 and 3. So Scarlett, thinking about the step number and how it relates to these, for step 43, how many blocks would I actually suspect there on the right? Good. Good. And in that case, Scarlett, how many total blocks are we talking about? "88," she says. Thumbs up, thumbs down. 88 blocks in step 43? No, Isaac, why not?
Wait, isn't it 44 plus 43?
Well, yeah, but plus the one in the middle, right?
Oh, yeah.
Brooks?
I think I have the equation.
Think you have the equation? We'll come back to the equation in a second. All right, graph or table. If we do step number n, so step n and then number of blocks, usually b in terms of n. Step 1 had how many blocks?
1 and 2 and 1.
4 total. Step 2? Step 3? What do we think step 4 will have? And we've already said we think step 43 has 88. So if we think about this in terms of what we studied yesterday, how are we getting from step to step? Brooks?
Is it n times 2?
I didn't ask for the equation. I said, how are we getting to the next step?
You multiply it by 2.
No. How are we getting from one step to another, Brooks?
Oh, you add 2.
Add 2, plus 2, plus 2, plus 2. So yesterday we gave that a name, right? What did we call that? When we add the same thing over and over again? Common difference. Okay, we'll come back to that in a second. Brooks, what's your equation?
N2 plus 2.
N times 2 plus 2. Now let's not say n2. We typically put the number in front of the variable. It's called a coefficient. So 2n plus 2. Do you guys notice anything about the common difference and where it ended up in the equation? Daphne?
As the plus, add part added
why would the thing we plus 2 plus 2 plus 2, why would that turn into multiplication over here? Why would it turn into a coefficient? When we add 2, add 2, add 2, if I tell you to add 2 5 times, do you actually do it? What do? You do multiplication, right? So repeated addition turns into multiplication. We're going to see that a lot as we do some of these patterns today. Whatever that common difference is should be turning into multiplication. Now, that doesn't tell us what to expect as far as the plus or minus something. For that, I typically come back to the table and I just ask myself, well, if I know I'm actually going to multiply by 2, what's 2 times 1? But I wanted it to be 4, right? What's 2 times 2? But I wanted it to be 6. What's 2 times 3? But I wanted it to be 8. So what do we have to do each time? Add 2 more, right, to compensate. And so that's where the plus 2 is coming from. Did anyone write the equation like this instead? N plus 1 plus 1 plus n? Does anyone know why I might write the equation that way? How am I thinking about the pattern if that's the way I write the equation? First of all, are those the same thing? Yeah, because we can combine like terms. The n's go together, n plus n is 2n. The 1's go together, 1 plus 1 is 2. So these are definitely the same. But where am I coming up with that n plus 1 plus 1 plus n thing? What do you think I mean? Isaac?
You're trying to find like a good high term.
No, I wouldn't say that. Daphne?
Like you're adding it onto one side and you're adding the one in the middle and then adding on the...
Good. So I'm thinking of it the way that Scarlett was thinking of it. This line here on the left is always the step number plus 1, right? Step number plus 1, step number plus 1, step number plus 1 every time. And so that's what I mean when I say n plus 1. That's the step number plus 1. And then the middle block just always stays literally one block, right? Plus 1 block, plus 1 block, plus 1 block. And then over here, we end up with the step number itself, right? Like 2 in this case, 3 in this case, 1 in that case. But again, that always ends up matching the step number itself. And so that's why down here, when I write it down, I once again see the step number. So if we think about this visually, we can kind of tell why we end up with these 2 n's every time. You can also do a little rearranging if you want. These can always be turned into smaller rectangles if we just take this block and move it up here, right? You can see it's just 2 towers that are the same height. Yes? Okay, so some good stuff to think about. Let's get into your homework. Take out your homework. No, no special explanations here. And I want us to think back to what we studied yesterday. Our recursive definition is that any given term in a sequence is equal to the previous term plus the common difference. And that's how we symbolize that. So this is what we call the nth term in the sequence. This was the previous term. And then, of course, this right here is the common difference. For this first sequence, 1, 4, 7, 10, what should I notice? Emma Ruth, what do you notice? 1, 4, 7, 10? plus 3, plus 3, plus 3, right? So to get the fifth term in the sequence, one way to do that would be to take the fourth term and add my common difference of 3, right? In other words, if I can tell I'm going up by 3, what's the next term after 10? So a sub 5 would be 13. What's the sixth term in the sequence going to be? 16. What's the seventh term in the sequence going to be? And so on, right? So again, a sub 5, a sub 6, a sub 7, this is what we call sequence notation. It doesn't mean we're raising a to the fifth power or something like that. It's just a way to indicate the fifth term of the sequence, the sixth term of the sequence, the seventh term of the sequence. But we're also supposed to write an equation here and then use that equation to come up with the 43rd term. Do I want to sit here and add 336 more times? No. Now, there are a couple ways to come up with the equation. One is precisely what we just did with the visual pattern already. When we know we're adding 3, adding 3, adding 3 over and over again, what's the equation going to look like? A sub n is clearly going to be 3 times n in some way. But the first term, what's 3 times 1? But we wanted it to be 1. What's 3 times 2? But we want it to be 4. What's 3 times 3? But we want it to be 7. So what am I doing each time after I multiply by 3? Oh, I'm subtracting 2. Let's check this out real quick. A sub 5, what's 5 times 3? Minus 2? Did it work? Seems to. 3 times 6? Hello? 18 minus 2? 3 times 7? Minus 2? So is the equation working? Yes. Now, although I think that's a good way to come up with the equation, it's not necessarily super reproducible. That is, if you get it, you get it. But if you don't get it, I'm not sure that that's going to be that helpful to you. And so this is where we go to what we learned again yesterday, what we called the explicit definition of a linear function, of an arithmetic sequence. A sub n is always equal to the first term in the sequence, a sub 1, plus n minus 1 times d. Now, let me say a little bit more about that, and then we'll come back to some of these examples. Okay, so again, what this means, and your notebook should be open if you need to take this as notes. That's a good idea. A sub n, we've already said several times, just means the nth term of the sequence. A sub 1 just means the first term of the sequence. Let's actually put that in symbols. First term. So notice n, 1, 1, right? The n itself, you might notice, pops up again over here. And then, of course, we have d, which is the common difference, right? The common difference. And as always, is the step number. Okay, so where does this come from? Why is this working? Well, let's consider something like 1, 4, 7, 10, 13, etc. 1 was which term in the sequence? Okay, so this is n, the term number. That was the first term, and then 4 was second term, and 7 was third term, fourth term, fifth term, etc. Remember, this is this would be a sub n. So a sub 1 is 1. A sub 2 is 4. A sub 3 is 7. That make sense? Okay. The first term is whatever it is. We can't really figure that out. But this 4, how did we come up with it? I mean, we were given it, but where is it coming from? Gray? Yeah, where's the 4 coming from?
+2.
What do you mean plus 2?
What?
What's plus 2? Oh, you mean the relationship there? As a coincidence, it is plus 2. That's true. Is this one plus 2? No, so that doesn't end up holding up, but look this direction, Gray.
Oh, it's +3.
Plus 3, right? So this was the previous term, 1, plus 3, right? And then what's this?
+3.
It was also the previous term plus 3. In other words, this one was 1 plus a 3 and another 3, right? Why have we used 2 3s now?
It's 2 steps.
Because we've taken 2 steps away. What's a 10?
1 plus 3 plus 3.
What's a 13?
1 plus 3 plus 3.
I want you to notice something. That is a 3 used 1 time, right? That is a 3 used 2 times, yes? That is a 3 used 3 times. And that is a 3 used 4 times. As we think about our step number, how does it relate to how many of the common differences we use? We always use 1 less common difference, right? That is what is going on here in our explicit definition. N minus 1 is counting how many of the common differences do we need. We always need 1 less than whatever the step number is that we're interested in. So for example, coming back over here, if I want a sub 43, one way to get that, other than just coming up with this equation and using it, would be to say, well, let's take whatever the first term is, and then how many common differences will we need for the 43rd step? 1 fewer than the step number, right? What's 1 fewer than 43? 42 of the common differences. Well, what was the common difference in this case? 3. So we can do some evaluation now. 43 minus 1 is 42. D is 3. And then where did this sequence start at? 1 was the first term, right? And so what is 1 plus 42 times 3? 127? If we came over here and if we had come up with this equation, a sub 43 equals, we said 3 times n, which right now would be times 43 minus 2. Is that also 127? 3 times 43 minus 2? Is it? No?
Yes.
Maybe? Well, which one, Gray? I mean, which one, Brooks? Which one?
Yes.
Yes. Definitely worked, right? Hello, Mr. McGee. Okay. So, again, this explicit definition is a way to guarantee we can come up with the equation, I mean, quite honestly, without having to think very much about what's going on. Like this 3 times n minus 2, we really kind of had to think about what was going on, but this explicit definition should work every time without much thinking at all. Take a look at number 2 to see what I mean. Let's just say I want to skip ahead right away to my explicit definition. It is always the first term plus the step number minus 1 times d. Well, in this case, What was the first term?
7.
7. And then, of course, the step number will be whatever it is, times a common difference of 5. Now, could we simplify that a little bit if we wanted to? Yeah, what's 5 times n?
5n.
And 5 times negative 1?
-5.
And what is 7 plus 5n minus 5?
5n.
What can we combine there?
5n
2
minus
times
2.
5.
A 5n and, not 2 times it, what's 7 minus 5?
2.
Plus 2. Now, for those of you who just kind of did it on your own, here's probably what you did. We know we've got 7, 12, 17, 22. How are these growing? Plus 5, plus 5, plus 5. That's the common difference, right? Plus 5. So what will the next term be? A sub 5 will be 27. And then the next term after that?
32.
5 more is 32. And then the next term after that? 5 more is 37. But if I want the 43rd term, I might have noticed, okay, so if I do a little table, n, a sub n, step 1 was 7, step 2, 12, step 3, 17, step 4, 22. If I'm adding 5 plus 5 plus 5 plus 5 over and over again, that ends up being multiplication, right? What's 5 times 1? But we need it to be 7. What's 5 times 2? But we need it to be 12. What's 5 times 3? But we need it to be 17. What's happening each time? We're getting too bigger, right? So for step n, it's going to be 5 times the step number plus 2, which you'll just so notice is where we ended up over here. William? Yes. So what's step 43 going to be? A sub 43 would be what?
43 times 5 plus 2.
43 times 5 plus 2, which is
217.
217. Seems right. 43 times 5 should be 215 plus 2, 217. Questions? What else do we want to do? Well, you tell me. What else do we want to do?
We do 6.
Really? Are you sure? 6 is easy. How are we changing here? This is weird.
Plus 4.
Yeah, it's plus 4 over and over again, right? If you think about it in terms of the explicit definition, it should actually be a little bit simpler here. So a sub n is just the nth term, of course. What's the a sub 1 right now?
X plus 3.
X plus 3. N minus 1 just always stays n minus 1. What did we say the common difference was?
4.
4. And so once we simplify that a little bit, 4 times n, 4 times minus 1, we get 4n minus 4 plus the x plus 3. And so what we end up with is the nth term in this sequence will be x plus 4n minus 1. Because positive 3 minus 4 is negative 1, yes? In that case, a sub 43 would be x plus 4 times 43 minus 1. Well, what's 4 times 43? 172 minus 1. And so what you should have come up with was x plus 171. What about the next 3 terms? What would those have been? X plus 19, x plus 23, x plus 27, right? I'll do one more. No? We're good? Okay. Should we turn it in, or do we think that's an A for everybody?
A for everybody.
A for everybody.
A for everybody.
A for everybody.
Turn it in.
A for everybody.
Y'all are bizarre. Maybe an A for everyone except for Isaac and Gray?
Yes.
I mean, gosh, Brooks. A for everyone. A for everyone.
I tried so hard.
But you've got a new worksheet. You guys see what I passed out?
Yes.
So let's work on that. We've got 20 minutes. Write the equation of a sequence in which the fifth term is 19 and the common difference is 4. So a couple ways you could approach this. We could make a quick table, n, a sub n. In this case, we know when we get to the fifth term, it's 19. And then we could count backwards. How do we count backwards in this particular case? Yeah, we would go minus 4. The common difference would be minus 4. Although, actually, I don't love that. That ends up getting a little confusing. Let's just think of it this way. Plus 4, plus 4, plus 4, plus 4. Actually, before I even do these other ones, how many common differences have I used for the fifth term? 4 of them, right? It's always one less. Well, the common difference is 4. What's 4 fours?
16.
If 19 is where I get to, but I know my common differences account for 16, what must I have started at? Must have started at 3, right? Let's make sure that works. 3 and 4 make 7 and 4, 11 and 4. Does that take us to 19? Now let me show you, technically speaking, what we were doing was this. We know, as always, a sub n is a sub 1 plus n minus 1 times d. In this particular case, we don't begin by knowing the first term. We don't necessarily know the step number yet, but we do know that the common difference was 4. So, if we simplify that a little bit, we get that a sub n should be the first term plus 4n minus 4. So far, so good? We're sure?
Wait,
Okay, Corbin, I'm waiting.
isn't it a sub 5 equals...
We're not going to do a sub 5 yet. I just want to state it for any term in the sequence. We'll do a sub 5 in a second. So any questions on how I've come up with this any term in the sequence definition? Corbin?
Yeah.
Okay, what do you
I
got?
don't know what it is.
Well, again, we always start with this. That's just something to memorize. And I don't know yet. I mean, we do. We're going to use 5 in a second, but we haven't used it yet. D, the common difference is 4. I'll tell you what, because this is confusing, let's go ahead and skip ahead. Let's do what Corbin is suggesting. We do know what term it is, right? We know that the fifth term in the sequence, so a sub 5, is going to be equal to the first term, which we do not know. I'm running out of room here. The first term,
So you always do the first term for that?
the explicit definition always has the first term, yes. But we don't know what the first term is right now. We're trying to figure it out. I'm trying to show you guys algebraically how we figure it out. Obviously, we did figure it out, right? What is it?
3.
It's 3. So we figured it out, but I want to make sure we can do this algebraically. So the fifth term is going to be the first term plus the step number minus 1. Well, what's the step number right now? No. 5, right? Times the common difference, which of course we said was what? 4. Well, notice we talked about 16 when we did this one over here, right? That's where the 16 is coming from. 5 minus 1 is 4 times 4 is?
16.
So what we end up with is a sub 5 equals whatever a sub 1 is plus 16. Now, last of all, do we know what a sub 5 is? What is it?
19.
19. So it must be 19. That's equal to a sub 1 plus 16. What does that mean about a sub 1? And so that's how we can say, oh, that first term has to be 3. If we put this all together, let's come back over here. A sub n for number 1 is going to equal the initial term. What did we just figure out the initial term was? 3 plus n minus 1 times the common difference of 4. When we simplify that, 3 plus 4n minus 4, what do we get?
4n minus 1.
And so that is what you should get for number 1, 4n minus 1.
So why could we do 4 times 1? Well, how I got it was
It's distributed.
I did 4 times 5, and then I subtracted 1, and
4 times 5.
that's how I got it.
So talk us through number 2, Gray. What would you do on number 2?
I do 5 times 4. 2 times 5 times 19 would give you something like 95.
So we know the 19th term is 4, and Gray is saying, okay, so let's just go ahead and do 19 times 5, which is 95. Go on.
And I did 95. What I did minus 86 as the first.
86?
Wait, 80. I don't really know what I got. But I got 5 n minus 91.
Well, yeah, where's the 91 coming from?
I think I
How do we get from a 95, Gray, to a 4?
subtracted 95 minus 4.
Yes, and you got?
91.
Yes. So Gray has noticed, oh, if the common difference is 5, we're definitely multiplying something by 5, so that's the 5n. But when he actually tried that with the 19th term, to go from 95, that's 19 times 5, all the way back to the actual 19th term of 4, he had to subtract 91. And so that's where Gray came up with his equation. So, okay, Gray, your method works great. For the rest of us, we are probably not going to want to make a table where we go all the way from the 19th term back to the first term. That's going to take a long time, right? So again, that's where the explicit definition comes into play. A sub n is always going to be a sub 1 plus n minus 1 times the common difference of d. In this particular case, I could say a sub 19 equals whatever a sub 1 is plus the step number minus 1, so 19 minus 1, times the common difference, which is 5. And you'll notice this almost exactly turns into what Gray did. What was the 19th term?
90.
Nope. What was the 19th term? It was 4, right? So what we say is 4 equals an unknown a sub 1 plus, what's 19 minus 1?
18.
And 18 times 5?
90.
So 4 ends up equaling a1 plus 90. And then you can subtract 1 on both, or 90 on both sides. What's 4 minus 90?
86.
So the first term in this sequence must be negative 86. If you take that back over here to the definition and plug everything in, you will eventually simplify down to Gray's same a sub n equals 5n minus 91. Isaac?
Couldn't the common difference be subtraction? And it could have been 94.
If I meant subtraction, I would have stated the common difference as a negative number. So no.
How do you get negative 86? So I got all the way up there, and then I did the plus the first term. I got 94.
No, we needed to subtract away the 90, not add it.
I did, to get negative 86, I did 5 times 1 minus 91.
That's fine. Daphne,
What particular way do we solve these?
any way you want. I'm showing you two different ways here. One of them I would consider more intuitive. That is basically every time we look at the common difference, we know we're going to multiply by that. So on number 3, I can already say a sub n is going to be 19n plus or minus something. And then I just try to figure out what's the plus or minus something. In this case, if I was doing Gray's method, what did we know about? The fourth term is supposed to be 5. Well, what's 4 times 19?
76.
So 19 times 4 is 76. But what was the fourth term supposed to be? 5, right? So 5 equals 76 plus some unknown amount. How do we find the unknown amount? Subtract the 76. And so we get that our unknown amount is negative 71. So when we come back over here for the definition of our sequence, it would end up being minus 71. So that's what I would consider the intuitive method. The less intuitive method is just plug it into the explicit definition and see what happens. Okay, so we ended up doing a few of those. I'm going to let you have the remainder of class today, 6 minutes, to work on the rest of the worksheet.